Hello. In this section, we are going to be looking at what are called probability distributions, which are just essentially probability tables. We're going to first start with something called a frequency table, which is just a count table, kind of something you're pretty familiar with probably. And we're going to work with a specific scenario and just kind of build up from there. So here's the scenario. Let's say that a gaming software company has 5 online games on the market and they're interested in how many games each of their customers play. So they survey 800 of their customers, just chosen randomly. Because they're a customer, the number of games that they have, did it say play? How many games each of their customers play? Go between 1 and 5. There's 0. There's never a 0 because they're all customers, so they at least play 1. So just read the table. For example, like 150 of their customers play 3 of their 5 games. 110 of their customers play all 5 of their games. So question number 1, find the probability that a randomly chosen customer plays 3 games. So let's let x equal the number of games played. So then the probability that x equals 3, the number of games equals 3, will be equal to, well, how many of their customers say that they play the game or play 3 games? 150. Out of how many people did they survey? 800. So there's 2 ways you could know that. You either know it's 800 because I said there was 800 people that were surveyed, or if you add up all of those totals, 130 plus 110 plus 150 plus 300 plus 110, it equals 800. So 150 out of 800 play 3 games, and that's going to leave us with a 0.1875, which is what, an 18.7% probability. So about 19% of their customers play 3 of their games. Question number 2, find the probability that a randomly chosen customer plays at least 4. So that's the probability that x is at least, means greater than or equal to 4. Well, that's the same as saying the probability that they play 4 or they play 5, because the most you can play is 5. The probability that they play 4, how many of them play 4? 300, so this would be 300 out of 800, or means add 110 out of 800. They're adding together, because it's a fraction with a common denominator, will give us 410 out of 800. Recall or means addition in probability, so something a little bit bigger than 50% turns out to be 0.5125. So about 51% of their customers play at least 4 of their games, 4 or more. So that's how a frequency table works. The downside of a frequency table, as you can kind of see, is I'm constantly converting to probabilities. You know, if I told the CEO, oh, like 110 out of the 800 customers that we surveyed play 2 of your games, like that doesn't mean it. Like 110 out of 800, the first thing that they're going to ask is, what is that as a probability? So it'd be much more useful if we converted these all to probabilities. You know, it'd be more useful instead of saying 110, if I said, what is 110 out of 800? 13.75, so about 14%. It'd be much more useful if I told the CEO about 14% of our customers are playing 2 of our games. That's much easier to grasp because we're used to dealing with percentages. So instead of a frequency table, we more often than not use a probability distribution or a probability graph. A probability distribution is essentially converting that table that we just had a second ago into probabilities instead of doing frequency counts. A probability graph is just a bar graph that displays the probabilities for each of the events. Properties of probability distributions. Each of the events, so each probability for each event, has to be between 0 and 1. I can't have anything occurring more than 100% of the time or with negative probabilities. That won't happen. So every single individual probability has to be between 0 and 1. And if I add them all up, they have to total to 100%, which is the number 1 as a decimal. So those are the 2 laws of probability. Each item has to occur between 0 and 100% of the time, and the total has to be 100%. So here's a probability distribution for the blood types of the general population. So 41% of the population has type A blood, 44% has type O blood. First thing I might be asked to do is show that the distribution is valid. So the first thing I need to do is check that each of these is between 0 and 1. So I just say that. I would say yes. Each probability is between 0 and 1. So that's checked. So Second thing I need to do is just make sure they add up to be 100%. So 41% plus 12% plus 3% plus 44% totals to be 100%. So you would say yes, totals to 100%, which is equal to the number 1 as a decimal. So that's how you show that it's valid. You have to check both of those conditions. Step 2 is asking us what's the probability of the following. What's the probability that someone has A or B blood? That'd be the probability of A plus the probability of B. Is there any overlap? Because if there is, I would need to subtract that off. There is not. You either have to have A or B. Nobody can have both A and B blood. There is a type of blood called AB, but that is different than having A and B blood. You can only have one type of blood. So this would be a 41% plus 12%, so 53% of the population has either A or B blood. What's the likelihood of not having O? There's 2 ways to calculate this. What's the likelihood of not having O? That's all of these ones. So the first thing I could do is just add up the probability of A plus the probability of B plus the probability of AB. That's one way of doing it. The other way is to do this. This is kind of the more clever way, is to say, what's the likelihood of having O? And then let's subtract that from 100%. That's called the complement in probability. If you take a full-on probability in stats class, you'll use that a lot. So maybe a more clever way is to say, let's find the likelihood of having O and subtract that from 1. So 1 minus the probability of having type O blood. The likelihood of having type O blood is 44%, so that means 56% have to have something not O, which is what all of those would be if you added them up. So it's a more clever way of doing when they ask not something, is to use what's called the complement. This is spelled the complement, E-M-E-N-T. It's different than if I'm saying like, hey, I like your shirt. That is complement, I-M-E-N-T. Last thing that they're going to ask us to do is make a probability graph. So A blood, B blood, AB, and O. So here we go. I have A blood, B blood, AB, and O. A blood was 41%, so 0.1. How high is the biggest one go actually? 44. Okay, this will be good. 0.2, 0.3, 0.4. Probably wise to put where 0.5 is, consistently right there. So the first one, 41%, so right here. A, and then B is 12%. AB, 3%. So be aware, 3% is not 30%. So right here. And then O, 44%. That's what the probability distribution would look like. It's probably wise to even write what all these are so people aren't guessing. That was what, 41, 12%, this was 3%, and this was 44. Otherwise, the whole point of a graph is to communicate information. Otherwise, it's not doing a good job of that. I'm going to ask you to try. The following is a study that was done by the PGA, the Professional Golf Association, to start to identify how they might be able to attract younger golfers. They wanted to see the probability of different age people playing golf. So the first thing is show that the distribution is valid, and then calculate the probability that a golfer is 45 or older. So first define your X variable. What is X measuring? It's measuring age. So pause the video now for maybe a minute and a half. Unpause it once you've had a chance to try. Okay, welcome back. The first things you need to do to show the distribution is valid is to show that all of these probabilities are between 0 and 1. So you'd say all between 0 and 1. There's nothing negative, nothing bigger than 1. Second one you should check is that these total to be 100%. Now I want the likelihood that somebody is 45 or older. So that would be this or this or this. I add them all up. 19% plus 12% is 31%, plus 17 more percent, 48%. So half their population is older than 45. That might say to them, maybe we should try to find ways to recruit younger people so that there's more interest in the sport for a longer period of time. Last thing we're going to do is to talk about another thing that people want when they get data is they want to know the average. So with that customer one with the number of games that their customers played, the CEO might say, what's the average number of games that our customers are playing? And it depends on if the information was given to you as a frequency distribution or if it was given to you as a probability distribution in term. Well, the process is the same, but it's more apparent with the frequency distribution. So we're going to start that way. So let's return to the first example we did with the video game, and let's calculate the average number of games played by a customer. So here's how we're going to think about this. There were 130 of the customers that said that they would play one of the games. So there's 130 customers that play one of the games. So one game is played by 130 of the customers. So there's the first one. This is where you'll start to see the pattern. 110 of the customers say they play 2 games. So that means those 110 customers really are playing what? 220 games. How did I do that? I multiplied those two. So this one, when I multiplied these two, it'd be 130. And then 110 of the customers play 2 games. So that means that they really play 220 games. I'm just going to fill out this table before I go writing this stuff down. Just jotting these down. 150 customers say they play 3 games. So how many games do those 150 customers play in total? Well, 150 times 3, those 150 customers are really playing 450 games because each of them are playing 3. 300 customers are playing 4 games, which means that those 300 customers are really playing 1,200 games. 110 of the customers are playing 5 games, which means those 110 customers are really playing 550 games. These are actually the number of games being played. So I'd have to add all of those up, and then I would divide by the total number of customers, 800. So I'm going to write out everything that we really did here, just to be more clear. So what did we multiplied each of these numbers to get the reds. So one game was played by 130 customers. 2 games was played by 110 customers. 3 games was played by 150 customers. 4 games was played by 300 customers. And 5 games was played by 110 customers. That total would tell me how many games were played by the 800 people surveyed. To get the average, I would have to divide by 800. And then that's what I'm going to do. I'm going to add all these up. So when I add all these up, what is that going to be? 130 plus 220 plus 450 plus 1,200 plus 550. There was 2,550 games played by those 800 customers. So 2,550 games played by those 800 customers, which means the average is the division of those two. Divide by the total of 800. It means on average, each customer is playing 3.1875 games, about 3 games. You'll see, though, that is not, a lot of people say, oh, it has to be the 300 because most were playing 4. No, that's the mode. The mode is 4 games, but the average is 3.1875. Also be aware the average doesn't actually have to be possible. Nobody can actually play 3.1875 games. The average is just a number. It's the average value. It's the middle balancing point when you consider all of the points in total. So 3.1875 is the average number of games. That's how you find the average if you're given a frequency distribution. What if, though, the information is already being converted to a probability distribution? So we're going to convert those into a probability distribution, and then we're going to recalculate it doing the same process. It's the exact same, though, actually. So let's go back to get a probability distribution. So 130 divided by 800. So this one right here would be 130 divided by 800. 130 divided by 800. That's going to be 0.1625. How many played 2 games? 110. So 110 out of 800 is 0.1375. How many played 3 games? 150. Is that right? Yep, 150. Divided by 800, 0.1875. 300, 0.375, and then the last one, 110, we already did that. It was this one again. So there's the probabilities. So, 18.75% play 3 games, 16.25% play 1 games. What if I had the following information? I need to get the average again. How would I do that? And especially if I didn't know how many people were surveyed. Let's say that information's already been conducted, and I just had this table. Well, you do the same thing. If we go back and see, what did we do? We took these two numbers and we multiplied them, and then we added them all up and we divided by the total number of customers. Now we're going to be dividing by the total probability, which will be 1. So how do we get this? Well, first we make a probability distribution. Now we're going to multiply these things. 1 times that. So 1 times 0.1625. It's the same thing we did on the other side. 2 times 0.1375 plus 3 times 0.1875. You get the idea. Plus 4 times 0.375 plus 5 times 0.1375. Go back and look. That's the same thing we did here with the frequency counts. It just might seem a little bit more strange because we're doing it with probabilities, but it's valid. Now we need to divide by the total. If I didn't know how many people were surveyed, I have to total by the column that I'm working with, its probabilities. What's the total of the probability column? It totals to be 1. So I just divide by 1. And then I run the calculation. And you can check, when you run this calculation, you're going to get the exact same thing that we did before, 3.1875. You have to. Another way of seeing that is this. If I go back to this right here, look at this. This is just 1, and then 130 over 800. Plus 2, 110 over 800. Plus 3, 150 over 800. Plus 4, 300 over 800. Plus 5, 110 over 800. Each of these are the probabilities. 130 out of 800 is 16.25%. 110 out of 800 is 13.75%. It's the exact same thing. So if they give you a probability distribution table, you just multiply by the corresponding, whatever the far left column is, the number of games, and then you add all the values up. So you multiply each of these individually, add them all up, divide by 1, you're still going to get 3.1875. So that's how you calculate an average if you're given a probability distribution. Besides calling this an average, you'll also hear this called an expected value. Expected value is what we expect. It is the average. The expected value is the weighted average of all of the variables. And how do we find it? We just multiply by its probability. So if I have a table, I just take each of these and I multiply by its probability. And once I have multiplied by all those probabilities, and then I add them all up. So example would be maybe a 6-sided die. What's the average roll for a 6-sided die? You can either get a 1, 2, 3, 4, 5, or 6. Each of them has a probability of 1, 6. So 1 times 1, 6, plus 2 times 1, 6, plus 3 times 1, 6, plus 4 times 1, 6, all the way down. Turns out the average roll for a dice is 3.5. So note that that's not actually possible. It's just the average roll. The average does not actually have to be possible. Like the average number of kids in the US might be 2.1. You can't have 0.1 of a kid, but it's the average. One place that this gets used, and I think this is our last example before I have you try one, is insurance. Insurance uses this to kind of set your policy amounts, your premiums. An insurance company has collected the following data on the probability of an accident costing a certain amount and is wondering what to charge for their 6-month policy. They expect that 1 out of 15 of their customers are going to have a $1,000 accident, so very small, minor fender bender. 1 out of 50 are going to have a more serious fender bender. 1 out of 150 are going to have pretty much an accident, and 1 out of 400 might have like almost a total. So what would the average cost be for all of their expected accidents? So I do the value times the probability. So this would be 1,000 times 1 in 15. So that's a 115. So 1,000 times 1 in 15 is 66.7. 5,000 times 1 in 50. When I multiply that, I get 100. 10,000 times a 1 in 500 chance, or sorry, a 1 in 150. That is 66.7. And then the last one, a $20,000 accident, 1 in 400. That's going to expect them to cost $50. And then the average, the expected value would be the total of all these. So if I add those all up, 66.7 plus 100 plus 66.7 plus 50, $283.40. That would be the expected value. That's how much they expect to pay out. Now think about it, if you're running the company though, that's how much they expect to pay out per person. So what do they need to charge? They need to charge more per person, otherwise they're losing money. So they're going to charge much more than this because they have to pay for their to run the company. They got to pay their own salaries for all their employees. They have to pay, running costs to have the company going, and then they got to charge a little bit more in case there's some bad months. Maybe there's a lot of accidents during the winter or things like that. So they might charge something like maybe even double this or like $500 or something more, but they need to charge at least that amount because that's what they expect to pay out per person. Going to have you try an expected value one. So Graduation Supply Company offers 5 items for a graduating senior. The school takes a poll to see how many each senior is going to buy. First, make a probability distribution, and let's say go out to 3 decimal places. So you need to make a probability distribution. I'll let you know that the first thing you need to do is find how many there were in total. So in total, I'll help you out there. There were 625. If you add all those up, there are 625 seniors polled. So you need to convert all of these to percents and then calculate the expected value. So pause the video now, maybe a few minutes, give everyone a chance to try, unpause it once you want to check what the answers are. Okay, here we go. First thing you need to do is convert to a percent. So 12 divided by 625, then 122 divided by 625, then 134 divided by 625. When you convert to percents, here's the values. Then you calculate the expected value by multiplying each of the number of items by their corresponding percents. So that times that, 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 that times that. Multiply all of those out, you'll get 6 values, and then you add them all up, and you'll find that the average senior bought 2.88 items. That is it. Thank you very much. Have a good day.